this presentation, I'm going to talk about cold forming automation, which is a project that I'm currently handling with Tile Industries Limited India. And before we get into the understanding of the project, what exactly is happening inside that, I would like to explain you in brief what exactly is cold forming with respect to watch manufacturing. And forming is basically a process wherein the metal is formed into the particular shape by forging it. And here in watch manufacturing, the brass or the steel, which is the raw material, is converted into the particular shape, the shape of the watch case that we wear, right? The outer shape. It can be round, a square, whatever it is. It is the process of converting the raw blank, into that particular shape through forging it. When we talk of cold forging, it is the metal is forged under the cold condition. There is other process called warm forging wherein you heat the metal and make the flow happen. So with respect to watch manufacturing, that's what cold forming is all about. So now, from an automation perspective, what are the challenges that are involved in cold forming, and what are the key issues that needs to be addressed to convert this manual intensive process into an automated one? And first of all, the biggest challenge with respect to watch manufacturing is in general, not just with the project called cold forming automation, in general, with any project that we take with watch manufacturing, the biggest challenge is it involves a lot of variants in terms of the components. It involves a lot of variants, like say there are close to 600 to 700 different varieties of watches. But if you take a automobile sector, or if you take any other sector for that matter, the number of variants is less. We see hardly one or two variants of vehicles, or we see one or two variants of motorbikes in India. But when you take watch, every individual has a different shape of watch, right? So those as a variant is good for the watch industry because the watch sells well. But for an automation engineer, it becomes difficult. It becomes difficult in designing the picking systems which would ensure that the pick and place takes place. So now this is the biggest challenge with respect to watch manufacturing. Handling the variants by the automation system and designing a system which is adaptable to frequent model changeovers has been the biggest challenge. Now, when it comes to cold forming automation, the challenge still remains. And in any project that we take with case automation cell and item, there is a basic funda. There is a basic structure in which we start conceptualizing the ideas for the project. I'm going to present you on that next. Yeah, this is it. Any project that we take evolves around these 10 steps basically. Starting with defining an objective for the project. What is this project going to take us to? And what are the key results that we can expect once this project is done? So, when we define an objective at the very first stage, we keep sky as the limit. We consider all possible options that are currently hindering us in manufacturing and say all this is going to be addressed by automation. So that is defining the objective. And once an objective is defined, for the particular automation, what is the concept which is going to support it, and how do you going to design it, and what are the trials that you're going to take with the concept, and ensure that this particular concept would ensure that the other objectives are satisfied. So that is the process of designing the concept. And once the concept is designed, we get into the trial run stage, because most of the concepts do work very well at the theoretical stage, but when it is practically implemented, there are a lot many challenges in getting it through. So this loop between the concept design and trial takes place, like I've been mentioned, in kind of a small loop here. And this process takes place, one after the other, until we achieve a concept which would completely satisfy the objective that we have defined. After this particular stage, and after these two particular stages are over, we get into the final objective declaration stage. And in final objective declaration, in most of the projects that we take, we start with a global objective. We say everything is possible, but once we get into the concept stage, we still find some hindrance, like maybe these kind of operations may not be possible. Only the automation is limited, the scope is limited, the cycle time is more, so we may not be using it for a mass production environment. Maybe we can use it for high-end products or something like that. So this final objective declaration comes in after careful discussion with the people from the shop, involving the shop in understanding how this automation is really helping their productivity and which part of their production shop they would like to automate. So the final objective declaration comes at the later part of the stage. Once the final objective is defined, the scope of the automation is defined, we get into the project execution stage where we would say this exactly is our role and this is what we are going to do as a concept. We have tested it and this needs to be substituted, and at the end of the day we also say all these things have to be done in this particular time, and it involves a cost and it involves a calculation of the return of investments. So all this stuff takes place in the project execution stage, and once that is done we deliver to our customers who are in turn our shop for managers or shop for people. And once that is done we get the feedbacks and corrections and say like there are minor adjustments, that is being deviated from the concept that we showed to the final thing that is running. So this takes place, and then the real production starts on the shop floor, and we support them in terms of what exactly, how exactly we can do one other stuff. And then at a global level, at a company level, we discuss on how the project has really added the value, and and will it get the return of investment in the proper time and other stuff. And once the value addition discussion is over, we get into the horizontal deployment mode wherein we multiply the projects in numbers and start deploying it throughout the shop. So this is not just with respect to the project called cold forming automation. It happens with any project that we take in case automation side. Now having said that, now let me take you through each and every modules of this overall structure with respect to cold forming automation to understand in detail what are the requirements for this particular project. And let me first start with defining an objective for cold forming automation. The first main objective is it should handle all the variants in automation from first forming to final forming. And what I mean here as first forming and final forming here is once a press blank is formed, it takes place in several stages. It not just happens in the first stage. It's like not that one time you press you get the particular shape, because the material what we're talking here are really hard. The brass and steel, the flowability of this material are really hard, and the presses that we use are like 150 tons. So it takes around 6 to 7 formings to get the required shape matching our desired dimensions. So this forming takes place at several stages, and whatever automation we design should be capable enough to handle all these stages, should be capable enough to handle all the variants in all the stages of the process. The reason is there are not there are no particular presses that is allocated which could take one particular forming. I mean, there's another kind of press which will handle the second forming. No, it's not that way, because every press is same, and what you change is the tool and the die set. With that, you form different formings, and the process takes place. So under this condition, automating a press which is costing close to 30 lakhs, you need your system to be capable enough to handle whatever load it is taking place, not just the first forming or the second forming of it. So that is very important here. And the second objective is to improve the productivity. Any system that we need to put in should improve the productivity. It should not decrease what is currently existing. So that is also more important. And improving the productivity means matching the cycle time and also um, giving the desired output per shift. And the next thing, by doing this automation, we also ensure that the operator's safety and morale is improved. Because when it comes to a forging shop, a press shop that we call as, there are a lot of accidents that happens, every now and then due to the carelessness of the operator. Now, any automation that we put in will take the man away from the operator and convert him into a supervisor for the automation rather than being an operator for the machine. So this condition would enhance this level, would improve the is quality of work and also the safety and morale of it. So, and the next is to establish the non-stop production for the entire shift period. That is also the biggest challenge, because automations are, frequently prone to stoppages. So, those automations should ensure that there are not much stoppages here, and it should also run freely. And the last is to establish an unmanned or an man uninterrupted end-to-end automation solution. This is also one of the things, because having a man to supervise an automation system should be the first part of it, but at the later stage of it, it should run even without the presence of the man. So these are all the overall objectives that we define even before we arrive at a concept and have the project is done. Because once you're clear with what you need to do, you can always find how you need to do it. So on those basis, we define the global objective of the project, and this is what the global objective of my project called forming automation. Now, once this objective is defined, I just get into designing the concept for the process automation. When it comes to the concept design, there are always two stakeholders here. One is the automation people, another one is the process people. But at the very first stage, since we are automation engineers, we start looking at it in a perspective that the process is always perfect. There are no changes that needs to be done in the process. Only you need to find a way to automate it. You make a system and attach it to the existing process. It should work because this approach is always better because when you take two to three problems in your head, it's always difficult to solve. And having a single problem is much easier. So, from an automation perspective, we assume that the process is perfect. No need, there is no need for changes to be done in the process side for the automation to run successfully. But in reality, it's not the case. Process needs a lot of modification to suit the automation. But when we start at the first stage, we go in this mode. Now, having said that, we start with three fundamental concepts that are more important in designing an automation system. First thing is designing your pick and place unit. Second thing is designing your gripping unit. And the third thing is your teaching method. Teaching method is how the operator interacts with the automation system and 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 integrate it with the process. That's called as teaching method. Now these three things are fundamentals in automation. And the first two things what I'm going to talk about, the picking unit or gripping unit, are merely the correct product selection. If you correctly select the product, from there it's easier to automate. So I'm going to talk you deep into these three things because this is not just technical. This is also very important from a project management point of view. How to select a project with what device and why we selected that particular way to get the desired results. That is also very important. Now, having said that, let me first get into the picking unit and what is the concept on which we want to build it. Basically, if you take picking units, there are in markets a lot of picking units, but all of them would fall under these three categories. One is you can have pneumatic slides. Another one you can have servo slides. The third one you can have an industrial robot. And all the systems are not the same because pneumatics can move from only two positions. It can go from A to B and B to A, and obviously it's actuated to R. When you take servo slides or robot, they are more or less the same. Only the way they look are different. And I'm talking in perspective of the way they operate are same because they move to different positions and they're also easily programmable and their speed can be controlled comparing to the pneumatic system. But it's all understood at this point of time what exactly pneumatic slide does or servo slide or robot does. But what it is important for us here is how do we choose a system where all of the system are capable of performing our desired operation. That is very important here. In general, we call all the systems as blind systems. The reason is all the systems needs to be taught those positions, whether it goes from A to B or A to B to C to D. All these positions need to be taught because we need to teach the robot or we need to teach the servo slide or we need to adjust the sensor and put this stopper block accordingly when it comes to pneumatic slide to determine all these positions. To teach the system what their positions are going to be, the initial and the final positions. So I'm going to call them as blind systems here because they're not capable of selecting their own position and moving. So when we have a blind system to automate, what we need is a perfect supporting system. What exactly is a supporting system? I mean here is it can be a vibratory bowl, it can be a linear feeder, it can be a gravity feeder, and all these three systems should do a job in inputting the component to the blind system in the perfect manner, in the same orientation, so that the blind system can do the job of pick and place easily, and it can do between this supporting system and the press. But the problem here, when with respect to watch case manufacturing, is that finding the suitable support system to match the number of variants that is available in the industry, right? Because as I already said, watch manufacturing involves a lot of variants and the batch quantity is also very less. So under this condition, these supporting systems, what they need to do here is they should be capable of handling all these variants out here. Not just one particular variant, they should be capable of handling all the variants. That's what the first point is. Any supporting system that we install should be capable of handling all variants, and most importantly, since our system is blind, it should output put the variance in the same pattern. That means I put in a triangle here, it should come out as a triangle. But when I put in the next triangle, it should also come out in the same way how the first triangle has come. Suppose it has not come, suppose there is a variation in degree, say 1 degree or 2 degree, this blind system will not know. It will obviously pick it from that location and load it on the die, which would cause a lot of severe damages to the existing process, and it will also uh, decrease the productivity. So that is a major threat here. The third point is the setting changeover between these different variants and maintain and the setting to ensure that the output pattern is same is going to take a lot of time. So there are currently not a system that we are able to find in the market or designed by ourselves which could satisfy all these conditions and which could handle all these variants for us, just because the nature of the variants are so high and the batch quantity is so less, it has become impossible for us to go for a supporting system and making our system in terms of pneumatic cylinder or a servo slide, making it a blind. So this option is something that is not feasible with respect to our manufacturing setup. So that is when we went in for the robots with vision. When it comes to robots with vision, it has an inherent advantage. The advantage is that it can take uh, components, it can pick components in any orientation, in any shape within the zone of the camera. So this advantage has I would say this advantage is our fundamental requirement considering the kind of variants that we handle in our shop floor. So now this gives a justification for us to get in whenever we start our automation project. We blindly started with the Epson with a robot and a camera, just because we know that we're going to end up in a situation wherein we need to handle a lot of variants, and it may not be possible for us to go for a supporting system like vibratory bolt, which would support us in outputting the components in the same pattern. So this gives a justification for us in selecting our picking unit. And next is going for the gripping unit. That's how the picking units is now selected. The reason for us to go for a robot and vision. And then when it comes to gripping unit, in market there are a lot of type of grippers, but fundamentally you can classify into two types. One is the vacuum suction type and another the pneumatic grippers. In these two types of grippers, um, what is important to us is the gripper, whatever we select, should satisfy three conditions. One is it should be capable enough to handle all the variants that we have, and also when it picks a component, it should ensure that it is picking in the same orientation, and the setting changeover between different grippers, different models, the grippers. Changing the gripper for different models should also be relatively easier. So these are the three conditions that we put forward in designing gripper system. As we know, there is a fundamental difference in robots when it comes to humans, because as a human, when a human does a pick and place job in manufacturing, he can pick the component in any orientation he wishes, and because of his sense of vision, he can correct the orientation while he approaches the placing point in the manner that he wants, in the manner relative to the way he has picked the component from the initial location. But for a robot to do that, it is not possible, because the robot vision would be present only in the picking zone. When it comes to the placing zone, it is again taught. It is blind when it goes to the placing zone. So the gripper system should ensure that the component is picked by the robot in the same orientation every time. Suppose I have this triangle here and I pick it with my robot. I should always ensure that I pick it in the same orientation. Suppose I pick, I just put my hand and pick with this vertices of a triangle. The robot should be capable enough to pick it in this particular orientation for any number of times, for any number of triangles. This is the fundamental requirement for the gripping unit. Having said that, uh, uh, going back to this vacuum suction and pneumatic grippers, what would suit us is a real question here. And it is very evident this vacuum suction technique would not suit us because of the nature of the vacuum cups, nature of the component which is hollow, which does not prevent us to which does not prevent the vacuum to get built up. So the obvious choice here is to go for pneumatic grippers. But if you take these pneumatic grippers are a standard product that is available in the street. There are parallel grippers, there are radial grippers, there are three jaw grippers, there are angular grippers, and many stuff. But these are standard products. Now, designing a gripper to hold a particular watch case is what the job of an application engineer like myself is. But the challenge here is there are different profiles, okay, and there are there are and these profiles are not of, I mean, prescribed dimension, because when you take a machined case, when you take anything that is machined, you can define the dimensions. But when it is under the forming process, it is basically the material flow. So the shape of the component in between the forming process would be undeterminable. I would say the flow would be undefinable even between one component to the other component. That is the nature of this forming process. Now, the only option that we have is pneumatic grippers, and with these grippers, we need to find a way to hold a component which does not have a defined dimension, right? When you take a final case, I mean, if you look at the watch that you have in your hand, whatever you have is a defined dimension watch. What I mean a defined dimension is whatever you wear it in your hand can be replicated into a diagram. You can say your watch is having this radius of, say, it is having a diameter of 10 mm or 15 mm, you can define it. But whether you can define it in between a forming process, no, because the metal would have flowed in those direction and you cannot define it. So in this undefinable portions, you need to hold it, and you need to hold it in a way such a way its orientation is not disturbed when it is picked, and until the point when it is loaded on the pressed die. So these are the conditions. Now, through our with our various researches, or I would say the various experiments, that would be the right word, the various experiments that we took for the past, 1.5 years with respect to designing a universal picking unit for any watch case, has resulted in three fundamental concepts. We have analyzed our models, and we say that we are models of watch cases, be it square or round or any shape, any watch shape, any damn watch shape. It can be held only in two particular ways. One is you can have a watch case and hold it from the outer. Second is you can have a watch case and hold it from the inner. These lines are, you can hold it in these areas, and whatever I have shown here, the holding thing are these pneumatic grippers. These pneumatic grippers having this parallel jaws, right? Now, in these two techniques, I would like to explain you in depth on them. First of all, and going for this outer concept was the biggest disadvantage to us, because what I've shown here in this picture is a proper rectangle. I mean, a proper shape. Even if you replace it with a square or a circle, it's a proper thing. But in the real time scenario in our production shop, what we get is not a proper shape. The shape would not be defined, because what we have here is a shape that is in between the stages of the forming. So when you take a metal that is getting formed at several stages, the shape that it takes would not be a defined one, because any extra metal that is not pouring into the cavity that is formed, would ooze out as a flash. And this flash, when it comes out, it will not take this defined dimension. So to make a gripper that would catch an undefined portion was the biggest challenge. And what we do here in an outer grip is to hold the outer part of it. And also in cold forming, the outer part is the region where this flash flows. So it becomes much more difficult, because when we talk about a robotic grip, whatever it is, the most important thing is to do the centering and orientation. So when you have an undefined shape, when you have a shape that is not defined on its outer edge, it is really not possible to center the component and the same time orient it in the manner we wanted. So that becomes a biggest challenge. So this particular concept was carefully discarded, considering the nature of flash that occurs in the process. Had it been, say, like a machine shop thing, had this project been somewhere else in the plant, wherein our definition of the case would be defined, like the process is over and the required dimension is achieved, then this concept would have helped us to a great deal. But right now, because of the nature of the process, this outer grip was something that we couldn't go forward. And also there was another biggest disadvantage here. It was like this weight balancing does not occur properly when you hold it in these areas, because if suppose there is more weight, there are some models which will be heavier on one side, and the other side it will be lesser weight. So considering those kind of models, this weight imbalance occurs, and when the robot is moving at high speeds, this component tends to tilt, turn, and then sometimes we have even faced problems where the component flies out. So these are critical issues when it comes to loading into a press, because the accuracy level of loading and unloading is in few microns, and these kind of errors have to be totally null, otherwise it didn't work for us. Now after that, we said, like, why shouldn't we try with an inner grip concept? But in inner grip concept, again we had some restrictions. The concept was very good because whenever you open a pneumatic finger, whenever you open a pneumatic gripper, what happens is, this kind of shapes that we have here, this kind of shapes that we have, automatically rotates towards a finger portion and gets locked along its diagonal. Whenever you take a square shape or a rectangular shape, any shape that has a proper diagonal towards it, what I have shown here is a proper diagonal, okay, and any shape that has a diagonal to it, and when you put in a pneumatic gripper inside it and open its fingers, what happens is this shape turns and self orient itself towards this longest diagonal, the diagonal that I've mentioned here. So this actually is a very good advantage, by nature, by inherent nature of the shape of the component. What we gain here is the centering and the orientation takes place automatically. But if you ask me whether this as a concept could handle all the variants, I would say no, because this concept of locking the component along its diagonals, I mean automatically locking the component along its diagonals, would hold good only for would hold good only for selected variants. What I mean here is would hold only good for these kind of shapes, would hold good for square, would hold good for rectangle and stuff. But for these kind of cases, what I mentioned here as special cases, say a rectangle, say a triangle, say a oval, with these kind of shapes wherein you don't have these diagonals, you don't have this opposite diagonals, it is not possible to hold it in that particular fashion. So again, there was one concept that we striked across, and the concept was also limited. It was not working for all the variants. Now it was high time for us to strike a concept wherein we would be able to handle all the variants. At that point of time, what we decided was to take a concept, I mean, wherein we do something like a locator and match the inner edge, I mean, match the inner dimension of the profile that we have. If we could do that, we would ensure that the component is held on the inner and we can hold it on the outer. To explain you more detailedly, what I've shown here is these are the special cases which I've shown here. I mean, these special cases. These special cases cannot be held by an inner grip because there are no diagonals here, right? Now, to hold these kind of special cases, what we did was, we took the inner shape over here and made a replica of it. We fabricated these pieces outside and we inserted this piece into this. This is actually our component, and what we have here is the locator, and this locator is attached to the robot arm, and this finger is also present next to it. Actually, it would be present in this particular manner. It will be present in this particular manner. So this piece as a whole is attached to the robot arm. Now what happens here is that when the robot moves towards this component, the vision locates the center of this component, and the locator that is attached to the robot arm is now inserted into it. Right? It's now inserted into it. Now once this is inserted into it, what happens is it prevents this component from moving from any direction, and it also orients and centers it. Once that is done, this gripper that is outside you know is used to clamp the component. What I mean by clamping here is through this pneumatic grippers we used to clamp this component. So by that doing that, we were able to take any component and orient it and center it with the same accuracy without much problem. So this is the concept is all about. We have this watch case over here. We make a replica of the inner profile, and we attach a pneumatic gripper around it, and this whole portion attached to the robot is now inserted into the watch case. The vision gives the dimension for inserting it into it, and this particular thing clamps it in the outside. So this as a concept help us to pick any given shape, right? But this concept of having a locator and centering the component uh, was giving us more advantage compared to the outer as was the inner grip, because this concept whatever we've shown here does the self balancing, does the weight balancing act by itself, because you know the whole area is covered here, whereas in this outer grip there are chances like the component can tilt, there was no weight balancing. And also this inner grip was capable of handling only shaped cases. It came with the shapes, cases with only having diagonals. But this was not a problem to us, because when you make grippers, when you make locators specifically to a component, it becomes much easier. The holding becomes much easier. Now, this is what I have summarized here. Inner grip can hold only particular shapes, whereas when you talk of a locator concept and outer grip, it can hold almost all shapes. You match any given inner ID and then grip it from outer, it becomes much more easier. Now, having said that, now the problem shifts from that, of how to hold a different component to how to make this locators happen. Now here, when we talk of a component that when you talk of a proper case, a proper defined case, once it is out of the forming shape, it is very much possible to make this locators, because these inner IDs, whatever we show here, are defined. Then you can actually go about in milling those locators and then attach it to the robot, which in turn would do the pick and place operation. But for the process of cold forming, wherein these inner shapes are not defined, because at the stage of forming, what happens is the material flows inner. So those cavities that are formed here are something that cannot be milled, or the cavity that are formed here, the dimensions are something that cannot be taken out, and a locator is literally not possible to be milled out. So that is when we said we wanted to make those locators easier. We wanted to make those locators at a faster pace, and we wanted to make our operator do it. It should not be a separate manufacturing process where you make the locators and attach to the robot to do the pick and place operation, because what happens here is a real-time production. And as I said previously, like the batch quantity that whatever we deal with are very few. It is like close to 100 numbers. So in those scenarios, these locators must be made in seconds, and it should also be remade and changed in seconds. So our focus from how to handle different components was now shifted to how to make these locators, which in turn would help us in holding different components. Now that is when we said this milling as a concept would not work to us, because milling, you can mill a component to define dimension, but in a case where I don't know what my inner shape is, where I cannot determine how the flow would be, it becomes really impossible to mill a locator. That's when we said, why shouldn't we try molding it? Molding as a concept was something that was not tried when it comes to making a locator. So when we scouted how to mold this component and what can be done with it, we said, like, we found that there were like two options to us. One was this epoxy molds, and the second was something called as fields metal. And these two things we identified as potential products which would give us the mold in no time. It would hardly take 5 to 10 minutes for us to get in these molds, and once that is done, it again becomes easier for us to attach it to the robot, to take different shapes and do the pick and place operation. Now, how these metals work and how these products work in taking their respective shape is something that is somewhat out of the scope, but I will just give a brief on this, how it actually does. What happens here is, like, this particular epoxy mold which I've shown here is a fast cast polyurethane. What a fast cast polyurethane does is, you have this resin and a hardener, and you mix it and you pour into your cavity. Say, like, this is my shape, this triangle is my shape, and what I do here is, like, I take this resin and a hardener and mix it and pour it into it. So once I pour it, within 5 minutes I get